Okay, we want to start off looking at chapter 15, simple harmonic motion. And we can think of simple harmonic motion as a repetitive motion, a motion that repeats itself about some equilibrium or middle position in this case. So just repeating itself above or below that position. This kind of periodic or oscillatory motion can be characterized in particular by a force. The force is equal to negative kx, so the force is proportional to the amount that this stretches from that equilibrium position. The more distance it goes, the more displacement it goes from that equilibrium position, the greater the force that is restoring it back towards that position. This force is called Hooke's law. So when the force is proportional to its position like that, by some constant, that is Hooke's law. This negative sign means that the force is always back towards the equilibrium position. So as this goes down this way, the force is pulling back this way, and as it goes above the equilibrium position, the force is pushing back towards that equilibrium position. This K is a constant, and it's called the spring constant or the force constant. It is an intrinsic value of the system. In this case, my system is the spring. By being intrinsic, that means it is a value that's not going to change. It is really characteristic of that system. So if I were to determine the spring constant of the spring, I could put the spring away for 2 months in a drawer and then take it out later after 2 months, and it would still be the same spring. It would still have the same spring constant. So it is indeed an intrinsic value of that spring. X is my displacement from equilibrium, equilibrium being that middle 0 point as the oscillation is going on either side of that point. Examples, as we just showed, is a mass on a spring. So this type of motion here is simple harmonic motion as it oscillates about some equilibrium position. Or a pendulum. This kind of motion, going back and forth about some equilibrium position as it goes back and forth, is simple harmonic motion. A string musical instrument, if I were to pluck a string on a musical instrument, that motion of the oscillation is simple harmonic as well. There are many systems that can be characterized as being simple harmonic motion. So we have a mass on a spring. A pendulum, like a child swinging on the swing, would be a pendulum. Or any kind of system that we can actually characterize using this restoring force where it oscillates about some equilibrium position. It could be torsional, like SpongeBob is so kind to demonstrate here. Torsional oscillation about some equilibrium position could be characterized as being simple harmonic. If I were to look at this motion as a function of time, say if I had this mass on a spring, and if I had a chart to chart this motion, and the chart were going by in a continuous way, so I could see this motion as a function of time, I would see that I would chart out a sinusoidal wave. So it would look like a cosine function or a sine function. It would be sinusoidal, and that would be the description of this motion as a function of time. Another way I could look at it is to put a motion sensor underneath this motion, and that motion sensor would also show a sinusoidal wave as a function of time. You will do that in lab number 1 for physics. If this force, this Hooke's law force, is the only force acting on this system, then by Newton's second law, I can say it's equal to the net force. So I could say that MA is equal to negative Kx. Now in this case, we might have gravity to consider, more on that later, but for the moment, we're just going to isolate this force as being our net force, and we're going to set that equal to MA. So our acceleration would be equal to negative k divided by m times x. k is a constant, m is a constant, so I have an acceleration that's proportional to my x. The acceleration gets greater in magnitude the further away from equilibrium I get. I'm just going to call this k divided by m omega squared. Why? We'll see in a moment. But for now, I'm just going to call it omega squared, omega being this W-looking Greek symbol. So acceleration is equal to negative omega squared times x, and we have defined omega squared to be equal to k divided by m, so omega is equal to the square root of k divided by m for a mass spring system. Since the acceleration is the second derivative of the position as a function of time, we have the second derivative of x with respect to time is equal to negative omega squared times x. This is a second order differential equation, and it has solutions of the form x is equal to a cosine omega t plus phi. So I can see by doing the mathematics of solving this differential equation that is describing our net force and our simple harmonic motion, that the solution is a sinusoidal function, like a cosine function or a sine function. If I change my phi, I can get a sine function out of my cosine. So here mathematically is a solution that shows that it should be a sinusoidal function as a function of time. How do I know that this is truly the mathematical solution? One way is I could plug it in. Let's take the derivative of this solution x as a function of time, the derivative of a cosine omega t plus phi, derivative of cosine is sine, and then by the chain rule I have to take the derivative of what's inside the function, omega t plus phi. Phi being a constant, that's going to just give me omega, so that's my derivative as a function of time of my position, which should be the velocity as a matter of fact. And then taking the derivative of that will give me the second derivative, the acceleration. The derivative of the sine is the cosine, and by the chain rule I have to take the derivative of what's inside the function as well, giving me another omega. So now I have a negative omega squared, a cosine omega t plus phi. But I recognize that the a cosine omega t plus phi is my x. So this is equal to negative omega squared times x. And just by substituting in, I have proven that a cosine omega t plus phi is indeed a solution of this differential equation. So since the solution fits, it must indeed be a solution. For simple harmonic motion as a function of time, I have this x equal a cosine omega t plus phi. This must repeat itself in a period of time. I know that if time were to go in such a way that what's inside the parentheses of the cosine function were to increase in total phase by 2 pi, then the cosine function will repeat itself. And at that point, my function will repeat itself. So, I will find that this sinusoidal function, as it goes through one cycle of the cosine function, will repeat itself in some time. And I'm going to call that time that it takes to repeat itself, I'm going to call it the period t. On the other sense, I'm going to also extend my function through an amplitude, either in the positive direction or in the negative direction, as my cosine function goes from positive 1 to negative 1. So mathematically, a gain in time of 1 period t should be equal to a gain in phase of 2 pi radians. So I should mathematically have this kind of expression right here. If I get rid of omega t on both sides, and get rid of a phase angle on both sides, I would have omega times the period is equal to 2 pi, or the period of repetition is equal to 2 pi divided by this omega value. Very good. So if I knew what omega was, I would know what the period of repetition is for my oscillation. And we define what we call the frequency as being 1 over the period. The frequency being how many times per second that this oscillation repeats itself. So the period is the time it takes to repeat itself from one position back to that same position. And the frequency is how many times per second this oscillation repeats itself. So it's 1 over the period. So now we define the angular frequency, omega, as being 2 pi over the period, or 2 pi times the frequency. So the angular frequency is 2 pi radians times the frequency. And that's what omega is. Since omega, for a mass spring system, we already determined to be a constant, square root of k over m, we now have that the frequency is omega divided by 2 pi, so that's 1 over 2 pi times the square root of k over m, and the period is 1 over the frequency, so that is 2 pi times the square root of m over k. What's interesting here is that if I had a mass spring system with a particular spring with a k constant and a particular mass with a certain value of mass, that even before I start an oscillation, I can know what the period of that oscillation will be, because the mass is already determined, the k is already determined, and by this expression down here, the period should equal 2 pi square root of mass over k. So the period of the oscillation, the repetition time, is going to be determined even before I start the oscillation, irregardless of the amplitude of the oscillation. So this is a good timekeeping device. I have a particular time associated with this repetition, and even if my oscillation were a small amplitude, it still has a repetition period, the same as if the oscillation were a large amplitude. The reason being that if the oscillation were a large amplitude, the restoring force would be larger, and hence bringing it back over a larger distance in the same amount of time as if the restoring force were smaller over a lesser distance. So it is a good timekeeping device, and lots of watches are based on this principle of a spring having a definite period. So we have our solution to our differential equation, x is equal to a cosine omega t plus phi. We can find the velocity of the mass by taking the derivative of our position as a function of time. We already did something like this earlier, and that derivative is a negative omega a sine omega t plus phi. And we can get our acceleration for all time by taking the derivative of the velocity as a function of time. And that we did earlier as well. And that will give us a negative omega squared a cosine omega t plus phi, where a cosine omega t plus phi is x. So this is our velocity, and our acceleration is a function of time. From this we can see that our maximum position for this oscillation would correspond to when the cosine function is maximum, and that's when it's equal to 1. So our maximum position is simply going to be equal to the amplitude this way, or the amplitude that way, negative a or a. If I take the absolute value, then our maximum position away from equilibrium is going to be equal to the amplitude a. Our maximum velocity will correspond to when the sine function is its greatest value, which is 1 as well. So our maximum value of the velocity will be omega times a, and it will occur when this oscillation goes through equilibrium. So I'm going to go down here, I'm going to momentarily stop, pick up speed as the force is pulling us back, maximum speed as I go through equilibrium, slows down, momentarily stops at the other amplitude, picks up speed, maximum speed as I go through that equilibrium position. And that's equal to omega times a. Our maximum acceleration will correspond to when the cosine function is also 1. And that will have a value of omega squared times A. And that will occur when I reach my maximum position, either away from equilibrium, either below or above this location. So my maximum position is A, my maximum velocity is omega times A, and my maximum acceleration is omega squared times A. So two things that are good to know are the angular frequency omega and A, because I can get all this information based on those two things. In summary, I have a position designated by A cosine omega t plus phi as my solution to a differential equation that describes simple harmonic motion. My maximum is A or negative A on either side. You could say the minimum position is negative A. The sine or cosine function can never be greater than 1 because of that. From omega, that's in front of the t, I can get two other things. I know that the period is 2 pi over omega, and the frequency is 1 over the period, or omega divided by 2 pi. So omega, which is characterized before my oscillation even begins, will help me characterize also the period and the frequency. If we know just one of these variables, omega, the period, or the frequency, we can get the other two very easily from these simple relationships. And the phase angle is the last thing I need to know. It is that fractional part of a cycle from which we start our time. We may not start our time at a nice position. We may be in the middle of a cycle. If I were to start this time when I pull this down at a maximum amplitude and start from there, then I would be using a cosine function with no phase angle. If I were to start my time when it passed through the equilibrium point, I could use this as a sinusoidal function equal to a sine function, because the sine function starts at 0 and goes from there. If I start anywhere in between, I need a fractional part of a phase angle to establish when I start my time. So that fractional part of a 2 pi cycle is my offset that allows me to start and solve this with a offset angle. So what can we observe from a waveform? Well, we know that peak to peak in either direction, we're going to go amplitude this way or amplitude that way. So if I didn't know where the middle point was, I would just measure peak to peak and divide by 2 to get my amplitude. And going peak to peak the other way in terms of time will give me the period. So I can measure those two things off my waveform. From the period, I can get, through these simple relationships, the angular frequency omega or the frequency. And with the amplitude measurement, I can get my maximum position, my maximum velocity, since that's omega times the amplitude, and my maximum acceleration, since that's omega squared times the amplitude. So I can get all this information from these two simple measurements. If I know the phase angle, which is my offset for the cycle period, then I can completely describe this waveform for all time. Let's try this out. Here's a problem. A spring stretches by 3.9 centimeters when a 10-gram mass is first hung from it. If a 25-gram mass is attached to the same spring and it oscillates in simple harmonic motion, let's calculate the period of this motion. So I'm going to start with the spring, maybe something like this. I come along and I put a 10-gram mass on it, and because of that, it stretches and establishes a new equilibrium position. So at this point, I know that the spring force Kx going this way is equal to the gravitational force mg going that way. So they're canceling out. But based on that fact, the fact that it stretched the distance x, I know that Kx equals mg, so my spring constant should be equal to mg divided by x. Since I put 10 grams on there, 0.01 kilograms times 9.8, and it stretched 3.9 centimeters, 0.039 meters, I get a K constant of 2.51 newtons per meter. Because of that initial stretch, I determined my K constant from that. And that's the intrinsic value of the spring. That's not going to change. All right, good deal. Now if I put a different mass on there, oh, and incidentally, because of this initial spring stretching and this weight on the spring, it will stretch, and that first stretch will offset the weight of this object. So I can establish an equilibrium position at that point, and hence any additional stretch of this spring from that point will be only due and causing a motion only due to the spring force. So gravity is taken out of the equation in this sense because of the initial stretch of the spring. The extra stretch is causing the simple harmonic motion. So that's why we ignored gravity earlier in our derivation. Okay, so I'm going to put a new mass on there, a 25 gram mass, and establish equilibrium, and then start my simple harmonic motion from that point. With the 25 gram mass, I would say that my angular frequency would be the square root of K over M. We just determined K, 2.51 newtons per meter, intrinsic value of the spring. Over this new mass, 25 grams, 0.025 kilograms, take the square root of that. That gives me the angular frequency of 10 radians per second. Based on that, my period is 2 pi over omega. 2 pi over the angular frequency, 10 radians per second, gives me a period of 0.628 seconds. So I could have established, even before I start this oscillation, that this system should have a period of 0.628 seconds. Great. Let's try another one. The position of a particle of a given is given by the expression x equal 4 cosine 3 pi t plus pi, where x is in meters, t is in seconds. Determine the frequency and period of this motion. Well, I have my position as a function of time and my amplitude out front. Whatever's in front of the t is my angular frequency. In this case, it's 3 pi. So just by looking at my solution here, I can establish that my omega is 3 pi. If I know omega, I can find the frequency, because the frequency is omega divided by 2 pi. So that's 3 pi divided by 2 pi, or 1.5 hertz. And the period. Period's 1 over the frequency. 1 over 1.5 is 0.67 seconds. Or 2 pi over omega would have been 2 pi over 3 pi, which would be 2/3, or 0.67 seconds. What's the amplitude of this motion? Well, whatever's out front is the amplitude. So we can just simply identify the amplitude as 4 meters. What's the phase constant of the motion? The extra constant inside the parentheses is the phase constant. In this case, it's pi radians. And what is the position of this particle at 0.25 seconds? Well, x describes the position of the particle for all time. So at a particular time of 0.25 seconds, I just need to plug that in. So my x is going to be equal to 4 times the cosine of 3 pi times 0.25 plus pi. And when I do this calculation, I better make sure my calculator is in radians mode, because that's what we're looking at in the cosine function here, radians. So I make that calculation, I come out to be 2.83 meters. All right, let's try another problem. A mass of 200 grams is connected to a light spring of force constant 5 newtons per meter, that's our K, and is free to oscillate on a horizontal frictionless track. So we're going to just do something like this with the spring oscillating horizontally. If the mass is displaced 5 centimeters from equilibrium and released from rest, find the period of its motion. So we're going to take this mass, pull it 5 centimeters this way, and release. If that's our t equals 0 point, then we would describe this as a cosine function with no phase angle. We want to find the period of its motion. We know the mass, and we know the spring constant, so we can find our angular frequency, which is one of the first things we want to find. So omega is square root of k over m. K is 5. M is 0.2 kilograms. Square root of 5 over 0.2 is 5 radians per second. Once we get omega, we can get the period. Period is 2 pi over omega. 2 pi over 5 will give us 6.28 divided by 5, or 1.26 seconds. Sounds good. What is the maximum speed of this mass? Even before I start the oscillation, well, I guess once I start the oscillation from 5 centimeters, because I have to know the amplitude, I can find the maximum speed. Amplitude is 5 centimeters, because that's how far we pulled it from equilibrium. And hence, our maximum speed is going to be omega times that amplitude. 5 radians per second times 5 centimeters, 0.05 meters, will give us a maximum speed of 0.25 meters per second. The maximum acceleration is going to be omega squared times the amplitude. 5 radians per second squared times 0.05 meters is 1.25 meters per second squared. Express the displacement, speed, and acceleration as functions of time. Well, our displacement is going to be a cosine omega t with no phase angle, because at t equals 0, we pull this out to maximum and we started from there. And the cosine function starts at 1 and goes from there at t equals 0. 1 this way. So we have a cosine function with no extra phase angle. Our amplitude is 0.05 meters, 5 centimeters. We have our omega we determined to be 5 radians per second. So here's our x for all time, 0.05 cosine 5t. The speed will be the derivative of x with respect to time. If I take the derivative of the cosine function, I get a negative sign, and take the derivative of what's inside, which will give me an omega outside, which will give me another 5. So this is going to be equal to a negative 5 times 0.05, which will be 0.25, sine 5t. And that's my velocity for all time. I can see that when the sine function is maximum, I get a maximum velocity of 0.25 meters per second, which we already determined to be our maximum velocity. Function. So I have a negative 1.25 cosine 5t. That's my acceleration for all time. So try this out. That's the end of lecture number 1 for this chapter. Look at a few problems. If you have any problems, look at the solutions for the selected problems online and in the Blackboard, and see if that helps you out.